The runaway sled, a force example problem involving interacting objects on an incline. A mom and her child are preparing to go sledding down a very steep hill, inclined 50 degrees from the horizontal. After seating the child in the sled, the mom loses her footing and slips. The sled and child, combined mass of 20 kilograms, slide without friction down the hill. The quick-thinking, 60-kilogram mom grabs a rope trailing from the sled and is dragged behind, with a coefficient of friction of 0.45. What is the acceleration of the sled while dragging the mom? Don't worry, nobody was harmed in the making of this physics example. So after reading and understanding the problem, this is the diagram that I came up with. I have a slope that's angled at 50 degrees from the horizontal. I've drawn a child in the sled and noted that that mass is 20 kilograms. Here's the mom being dragged behind with a mass of 60 kilograms. The sled is frictionless, but the mom slides with a kinetic coefficient of friction of 0.45. So now I'm going to create my free body diagrams. I'm going to begin with a diagram for the kid. So this dot represents the kid. The kid has weight, which points straight down. The kid has a tension force that's from dragging the mom behind. That points straight up the hill. And then the kid also has a normal force that should point straight along this axis that's normal to the hill. And so that'll be normal force. I need to distinguish that this normal force belongs to the kid and this weight belongs to the kid. Because when I get to the mom also has a weight which points straight down. So this is the weight of the mom. There's also a normal force for the mom. The same tension that the sled feels is the tension that the mom feels, except in the opposite direction. And the mom has the force of friction, and it's kinetic friction because she is sliding. Next up, let's make a table of forces. Alright, I've got my tables all written, ready for some values. Beginning with looking at the kid's case. The weight of the kid is equal to the kid's mass times the gravitational acceleration, so 20 kilograms times 9.8 meters per second squared. Altogether that equals 196.2 newtons. However, this weight force is not along either the normal axis, which I'm going to call the y-axis, or the slope axis, which is called the x-axis. It's in between, which means it has both x and y components. So if I'm going to look at the x component that runs along the slope, the angle, the 50-degree angle, is between that weight vector and the y-axis. So that x component, I can find that by using the sine of the angle. So 196.2 newtons times the sine of 50 degrees is a negative, because it points to the negative x-axis, 150.3 newtons. In the y direction, there's a y component along the y-axis. I'll solve for that using the cosine of that 50-degree angle. It's also a negative number since it points in the negative y direction. So 196.2 newtons times the cosine of 50 degrees, I get 126.1 newtons. The normal force I don't know offhand. Normal force can only act normal to the hill, and so it only has a y component, and it is positive. So I'll just label this N with a K for the kid, and we will have to solve for that using an equation. The tension force does not point normal to the hill. It points along the hill. That's only in the x direction. And I don't know the value. I'm going to have to solve for that. So I'll put in a T. The net force in the y direction, I expect a zero net force. I do not anticipate any acceleration either into the hill or up off of the hill. In the x direction, the net force is probably not zero. There probably is some acceleration. And so the sum of all the forces in the x direction will produce an acceleration equal to the mass of the object. This is the kid, so that's a 20 kilograms, times the acceleration. Now we switch over and take a look at the table for the mom. The weight of the mom is the mom's mass times the acceleration due to gravity, 9.8 meters per second squared. And so for a total, I get 588.6. That's in newtons, and that comes from the 60 kilograms times 9.8 meters per second squared. Now again, just like with the kid, this weight vector is not along either axis, it's in between, which means it has components in both x and y. The x component I will again solve by taking the sine function of the angle and multiplying by that hypotenuse, which is 588.6. It points down the hill, which is going to be a negative 450.9 newtons. So that comes from 588.6 newtons times the sine of 50 degrees. The y component we're going to find by taking the cosine of the angle. So 588.6 newtons times the cosine of 50 degrees is going to produce 378.3 newtons. Again, that's negative because it points in the negative y direction. So 378.3, and that's in newtons. The normal force, I'm not going to assume anything about it. We can solve for it if we need it. Normal force of the mom. Then the tension points down the hill this time, so I put a negative t in the x column, 0 in the y. The friction force points uphill, so it's going to have a positive value, and I don't know right now what the value is, but I do know the coefficient, which is 0.45, and I know that if I multiply that by the normal force on the mom, that will give me my force of friction. There's a 0 in the y direction there. In the y direction, just like before, I do not expect any acceleration. In the x direction, I do expect an acceleration, so the sum of the forces in the x column should all add up to produce a force that's equal to the mom's mass, which is 60 kilograms, multiplied by her acceleration. So next, let's go ahead and build our equations from our tables and solve them. So I'm going to begin by setting up my equations on this step. Now, a tip I've learned is that I look for columns with the smallest number of things, and so these are the y columns. Now I know the mom's force of friction depends on normal force, and it looks like in the y column I can solve for the mom's normal force. So that's where I'm going to start. So the way I build my equations is I just work down the column for all the individual forces. So negative 378.3 newtons plus the normal force on the mom plus 0, which I'm not going to write, but you can always write those down, is equal to the net force. The net force is the sum of the forces, and that happens to be 0. So what I've learned here is that the normal force on the mom is equal to 378.3 newtons. Now I can use that to find the force of kinetic friction on the mom, and I can write my equation from this x column from the mom. So here's what this looks like. Again, just work down the column. So negative 450.9 newtons plus 0, subtract the tension, add the kinetic friction force, which is going to be 0.45 times this normal force of 378.3 newtons. Multiplying them together, I get 170.2 newtons. And that is all equal to 60 kilograms times the acceleration. Well, I'm kind of stuck. I've got two numbers here, which I can combine, but I don't know the tension. So let me go ahead and combine those. I'll simplify this, and then we'll go after the tension. So negative 450.9 plus 170.2, that gets me a negative 280.7 newtons minus tension is equal to that 60 kilograms times the acceleration. So I have one more equation that has tension in it, and it's here in the x column of the forces acting on the kid. So let's go ahead and take a look at that equation, and then I might have some idea how to get around this problem of two unknowns. I don't know tension and I don't know acceleration. So here's what that equation looks like. I start at the top. I have negative 150.3 newtons plus tension equals, in this case, it's the mass of the kid, because this comes from the forces acting on the kid, times acceleration. Now it's key to recognize that these tensions are the same and these accelerations are the same. So if I solve this equation on the bottom, which came from the kid's force table for tension, I can plug it in and solve for acceleration. So that's what we're going to do in the next scene. So here's the equation we got from the forces acting on the kid. We can rewrite it and solve for tension by adding 150.3 newtons to each side. Now we're going to use this tension and plug it into the equation that we got from the forces on the mom. Now that I've done this, I need to organize this equation so that I have like terms on each side. So I'm going to have the negative 280.7 newtons. And then from inside our substitution, I've got this 150.3 newtons, and it's going to be subtracted. So subtract 150.3 newtons. I am going to move this 20 kilograms times acceleration to the other side so that the accelerations will be on the same side of the equal sign and separated from things that don't have acceleration in them. Because of this negative sign out in front here, I'm going to add the 20 kilograms times acceleration to both sides. So I've already got, over on the right-hand side here, 60 kilograms times acceleration, and then I add to that 20 also times acceleration. Now I just need to combine these numbers. And with combining those like terms, I'm ready to solve for the acceleration. Now I notice that I have a negative sign on the left-hand side of the equals sign, but no negative sign on the right-hand side. This means I'm going to get a negative acceleration, which is okay, because negative in my coordinate system was downhill, and that's definitely the way that I would expect this whole system to go. So my final answer here is going to be a negative 5.39. Newtons divided by kilograms will leave me with meters per second squared. And that is the final answer. That's the acceleration of the sled and the mom together heading down the hill.